As you listen to these words, the universe is dying. Every star you see is burning down to nothing. Every galaxy is racing from its neighbors, accelerating toward eternal isolation. Scientists have calculated how it will most likely end, and the timeline stretches so far into the future that human language lacks words to describe it. Timescales where 1 trillion years pass like a single heartbeat, where black holes the size of solar systems evaporate into whispers of radiation, where the last atom in existence decays into pure energy and vanishes into infinite darkness. The universe will not end with an explosion. It will end with silence so complete that the concept of sound becomes meaningless. Every scientific calculation points to the same terrifying conclusion. Everything that exists will eventually cease to be. If you want to follow the complete timeline towards the universe's end, please like and subscribe. This journey will change how you see every star in the night sky. Let's begin. Look up at the sun tomorrow morning. That blazing sphere of nuclear fire has burned for 4.5 billion years. It watched over Earth as the first single-celled organisms appeared in primordial oceans. It warmed the planet as dinosaurs ruled for 165 million years. It continued burning as early humans learned to make tools and eventually build civilizations that could study its light through telescopes. The sun seems eternal. Ancient cultures worshipped it as a god. The Egyptians called it Ra and believed it sailed across the sky in a golden boat. The Greeks named it Helios and imagined a chariot of fire pulled by immortal horses. Modern humans take its presence for granted, assuming it will rise every morning until the end of time. They are wrong. Confirmed astrophysical calculations reveal that our sun has approximately 5 billion years of fuel remaining. This sounds like an incomprehensible span of time. 5 billion years ago, the most complex life on Earth consisted of single cells floating in ancient seas. 5 billion years from now, humans will either have spread across the galaxy or vanished entirely from cosmic history. Yet in cosmic terms, the sun has already burned through roughly half its hydrogen reserves. The nuclear furnace at its core is running out of fuel. We exist at the midpoint of our star's life. The second half has already begun. What happens when the fuel runs out will destroy everything humans have ever known. Every city, every monument, every fossil, every trace that intelligent life ever walked upon this world. The sun's death sentence hangs over Earth with absolute certainty. Deep within the solar core, temperatures exceed 15 million degrees. At these extreme conditions, hydrogen atoms are stripped of their electrons and slam into each other with enough force to overcome their natural electrical repulsion. The nuclei fuse together to form helium, releasing energy in the process. This energy takes nearly 200,000 years to reach the surface. It bounces from atom to atom through the dense solar interior, gradually working its way outward through convection and radiation. When it finally emerges, it radiates into space as the light and heat we observe. Every second, the sun converts 4 million tons of matter into pure energy through nuclear fusion. 4 million tons, vanishing into radiation every single second. The sun has maintained this consumption rate for 4.5 billion years without pause. But hydrogen is not infinite. The sun has already consumed enough hydrogen to make over 100 Earth-sized planets. If you could gather all the hydrogen the sun has burned since its birth, you would have enough material to build a small star system. This cosmic consumption continues without pause, steadily depleting the fuel supply that powers our star. The numbers become almost incomprehensible when you consider the full accounting. The sun began its life with approximately 2 billion tons of hydrogen fuel. It has already converted roughly half of this supply into helium through nuclear fusion. But the sun will not burn steadily until suddenly extinguishing. Stellar death is a gradual process. a transformation that begins subtly and accelerates into catastrophe. The changes have already started. The Sun today burns slightly brighter than it did when Earth formed. It will continue brightening as it ages. As hydrogen in the core diminishes, the nuclear reaction rate decreases. Gravity, always pulling inward, begins winning its ancient battle against outward radiation pressure. The core contracts under its own weight, heating up as gravitational energy converts to thermal energy. This heating triggers hydrogen fusion in a shell surrounding the now helium-rich core. The additional energy production causes the outer layers to expand dramatically. The Sun begins transforming into something humanity has never witnessed up close, a red giant. The transformation does not happen overnight. It unfolds across hundreds of millions of years. First, the Sun swells slightly, then more, then dramatically. Its colour shifts from yellow-white to orange to deep red as the expanding surface cools. Over the next 1 billion years following core hydrogen depletion, the Sun will swell to more than 200 times its current diameter. Picture this if you can. The Sun currently measures 865,000 miles across. As a red giant, it will exceed 170 million miles in diameter. Its surface will extend past Mercury's orbit. The innermost planet will be engulfed by the expanding stellar atmosphere and vaporized. Then the Sun continues growing, past Venus. The second planet suffers the same fate. Swallowed by a star that once seemed so distant, the red giant Sun may or may not engulf Earth directly. Scientists disagree on the exact expansion. Some models suggest the Sun will extend just past Earth's current orbital distance. Others predict it will fall slightly short. But the distinction hardly matters. Long before physical engulfment, Earth becomes uninhabitable. As the Sun expands and brightens during its approach to the red giant phase, surface temperatures on Earth will exceed the boiling point of water. Oceans will evaporate into space. First as water vapor that greenhouse effects trap in the atmosphere. Then as the atmosphere itself is stripped away by intensifying solar wind. The timeline for this destruction begins surprisingly soon on cosmic scales. Within 1 billion years, the Sun's luminosity will increase enough to trigger a runaway greenhouse effect on Earth. Surface temperatures will rise past the point where liquid water can exist. Life as we know it has roughly 1 billion years remaining. Regardless of what humanity does in the meantime, 1 billion years. This sounds impossibly distant. Yet consider that complex multicellular life has existed on Earth for only about 600 million years. The age of mammals began only 66 million years ago. Homo sapiens appeared roughly 300,000 years ago. Human civilization spans only 10,000 years. Earth's remaining habitability window exceeds the entire history of complex life by nearly double. Yet it remains finite. The countdown has already begun. The red giant phase itself lasts approximately 1 billion years. During this period, the Sun's outer atmosphere becomes unstable. Massive stellar winds blow material into space, creating expanding shells of gas that glow with the energy of the dying star. Astronomers observe these structures around other stars and call them planetary nebulae, though they have nothing to do with planets. The name comes from early telescopic observations that confused these expanding gas shells with the fuzzy disks of distant planets. The misnomer stuck, despite its inaccuracy. Planetary nebulae display some of the most beautiful structures in the cosmos. Shells within shells, rings and jets, and spirals of glowing gas. Each one represents a sun in its death throes. Each one was once surrounded by planets that may have harboured life. The Cat's Eye Nebula, the Ring Nebula, the Helix Nebula. These stunning objects scattered throughout our galaxy are stellar graveyards, monuments to suns that burned for billions of years before finally exhausting their fuel. When enough mass has been ejected, The remaining stellar core can no longer sustain fusion. Nuclear reactions cease permanently. What remains is a white dwarf, a ball of matter roughly the size of Earth but containing most of the Sun's original mass. The transition from red giant to white dwarf happens relatively quickly on cosmic scales. Over perhaps 100,000 years, the outer layers disperse into space, the core contracts and heats, eventually reaching temperatures exceeding 100,000 degrees at its surface. Far hotter than the current Sun, white dwarfs represent the corpses of stars like our Sun. They generate no new energy through fusion. They simply radiate away the thermal energy accumulated during billions of years of nuclear burning. Slowly, inexorably, they cool. A white dwarf starts its existence glowing blue-white hot, intensely luminous despite its small size. Over billions of years it cools to yellow, then orange, then red, then, finally, to temperatures below what any telescope can detect. The cooling process takes longer than the current age of the universe. The white dwarf that our Sun will become contains some of the most exotic matter in the cosmos. Electrons stripped from atoms are packed so tightly that quantum mechanical effects support the structure against gravitational collapse. This electron degeneracy pressure prevents further compression, regardless of cooling. A teaspoon of white dwarf material would weigh approximately 15 tons on Earth. The density exceeds anything we can create in laboratories. Yet white dwarfs are common objects. The nearest one sits only 8.6 light-years away, orbiting the star Sirius as a dim companion to the brightest star in our night sky. But white dwarfs are not the end of stellar evolution. They are merely one category of stellar death. More massive stars face far more spectacular demises. Stars 8 times more massive than our Sun do not become white dwarfs. Their cores grow heavy enough to collapse beyond the white dwarf stage, triggering catastrophic explosions called supernovae. These cosmic detonations outshine entire galaxies for brief periods, creating shock waves that trigger new star formation in surrounding gas clouds. The physics of supernovae involves forces and temperatures that dwarf anything in human experience. When a massive star exhausts its nuclear fuel, the core collapses in less than a second. Material falls inward at speeds approaching 1/4 the speed of light. The density increases until atomic nuclei merge together. Protons and electrons combine into neutrons. The entire core becomes a ball of nuclear matter. This collapse releases gravitational energy equivalent to the Sun's total output over its entire 10 billion year lifetime. Released in approximately 10 seconds, the energy rebounds outward, tearing the star apart in an explosion that briefly outshines 300 billion suns. Supernovae create and distribute the heavy elements necessary for rocky planets and biological life. The iron in your blood was forged in a supernova explosion, the gold in wedding rings, the uranium in nuclear reactors. All these elements formed during the brief moments of stellar death. Supernovae leave behind either neutron stars or black holes depending on the original star's mass. Neutron stars pack more than the Sun's mass into spheres only 12 miles across, a city-sized ball of matter so dense that gravity warps space around it. Black holes compress matter so completely that nothing can escape their gravitational grip, not even light. The boundary marking this point of no return is called the event horizon. Anything crossing this threshold vanishes from the observable universe forever. Yet even supernovae represent only brief moments in cosmic time. The more profound question concerns what happens when all stars die, not just our Sun, but every star in every galaxy throughout the observable universe. Current observations confirm that star formation continues throughout cosmic space. Gas clouds collapse under gravity, fragment into protostars, ignite nuclear fusion in their cores. New stars are born every day across the universe. The Orion Nebula alone is forming thousands of new stars right now, but this stellar birth rate is declining. The universe has already consumed most of the hydrogen gas available for star formation. Galaxies have converted vast reservoirs of primordial gas into stars over the past 13 billion years. What remains is being depleted at rates faster than cosmic processes can replenish. When the universe was young, star formation proceeded at rates 10 times higher than today. Galaxies blazed with newborn stars. Supernovae exploded constantly. Heavy elements accumulated rapidly. The cosmos was a violent, dynamic place of constant stellar birth and death. Today, the universe has matured into middle age. Star formation has slowed considerably. Many galaxies have exhausted their gas supplies entirely. They drift through space as collections of aging stars with no new generations forming. Scientists estimate that star formation rates have declined by roughly 90% since their peak several billion years ago. The universe is past its prime. Most stars that will ever exist have already been born. This decline will continue. As remaining gas is consumed, star formation will slow further, eventually stopping entirely when no suitable gas clouds remain. The last generation of stars will form perhaps 100 billion years from now. After that, no new stars will ever ignite. The last generation of stars will be fundamentally different from the suns we observe today. As heavy elements accumulate in interstellar gas through successive stellar generations, the physics of star formation changes. Future stars will form from metal-enriched material with different fusion properties than primordial hydrogen. More importantly, the final stars will be almost exclusively red dwarfs. Red dwarfs are the smallest, coolest, and longest-lived stars in the universe. They burn hydrogen so slowly that their lifespans extend into trillions of years. A red dwarf born today will still be shining long after every other type of star has died. These stellar misers conserve their fuel with incredible efficiency. While our Sun converts 4 million tons of hydrogen per second, a small red dwarf might process only a few thousand tons per second. The reduced consumption rate extends their lifetimes by factors of thousands. The smallest red dwarfs, barely massive enough to sustain hydrogen fusion, can burn for over 10 trillion years. This exceeds the current age of the universe by a factor of 1,000. These cosmic survivors represent the universe's last light sources. Red dwarfs are also the most common stars in the universe. Approximately 75% of all stars are red dwarfs. They far outnumber stars like our Sun, yet they are so dim that not a single red dwarf is visible to the naked eye from Earth. Despite being everywhere, they hide in darkness. Proxima Centauri, the nearest star to our solar system, is a red dwarf. It orbits the Alpha Centauri system at a distance of 4.2 light-years. Despite this cosmic proximity, it remains invisible without telescopes. Its total light output is less than 1% of our Sun's. Red dwarfs also exhibit violent behavior despite their cool temperatures. Many produce powerful flares that can sterilize any planets orbiting nearby. The habitable zones around red dwarfs lie so close to the star that any planet there becomes tidally locked, one face eternally roasting, the other frozen in permanent night. Whether life can exist around red dwarfs remains an open question, but their longevity makes them the final bastions of stellar light in the aging universe. But even red dwarfs eventually exhaust their fuel. The laws of thermodynamics guarantee that no energy source can burn forever. Every red dwarf will eventually convert all available hydrogen into helium, ending nuclear fusion permanently. Scientists have calculated when the last star dies. The number is so large it requires new notation to express. 100 trillion years from now, roughly 10,000 times the current age of the universe, the final red dwarf will exhaust its hydrogen fuel. Nuclear fusion will cease everywhere in the cosmos. The stelliferous era, the age of stars, will end. 100 trillion years. Written out, this number contains 14 zeros. 1 followed by 14 zeros. 100,000 billion years. 10,000 times longer than the universe has existed so far. Picture this moment if you can. For the first time since the Big Bang ignited nuclear processes, no stars shine anywhere in the observable universe. The darkness is absolute, complete, everywhere. No new stars will form because no hydrogen gas remains in configurations suitable for gravitational collapse. The cosmic fuel supply has been permanently exhausted. Every fusion-capable gas cloud has either formed into stars or dispersed beyond recovery. The factories of starlight have closed forever. Every galaxy that once blazed with hundreds of billions of stars becomes dark. The spiral arms of the Milky Way, now merged with Andromeda into a single elliptical galaxy, contain only stellar corpses, white dwarfs cooling toward absolute zero, neutron stars spinning down to stillness, black holes drifting through eternal night. The Andromeda galaxy approaches us right now at 250 miles per second. In 4.5 billion years it will collide with the Milky Way. The merger will span billions of years. Stars will be flung into new orbits. Gas clouds will compress and trigger bursts of star formation. The two spiral galaxies will combine into a single elliptical structure. Astronomers have already named this future galaxy Milkomeda, or sometimes Milkdromeda, a hybrid name for a hybrid structure. By the time the last stars die, Milkomeda will have aged for nearly 100 trillion years. Its trillion stars reduced to cooling embers and collapsed remnants. This transition from light to darkness takes place gradually on cosmic timescales. The last stars do not extinguish simultaneously. They flicker out one by one across billions of years as individual fuel reserves run dry. But eventually, inevitably, the final nuclear furnace burns its last hydrogen atom. Somewhere in some galaxy at some moment 100 trillion years from now, the final red dwarf will exhaust its core hydrogen. Its outer layers will contract slightly. The temperature will drop. The dim red glow that sustained it for trillions of years will fade. And then vanish. The silence that follows is unprecedented in cosmic history. For 100 trillion years, starlight illuminated the universe. Photons travelled across vast distances, carrying energy and information between cosmic structures. After the last star dies, this stream of light ends permanently. No more sunrises on any world, no more starlight falling on any surface, no more stellar nurseries creating new suns, no more supernovae enriching interstellar gas with heavy elements. The cosmic engine of star formation and stellar death that drove universal evolution falls silent. Yet the death of stars represents only the beginning of cosmic ending. The universe does not simply stop when stars cease shining. Far stranger processes await in the darkness that follows. The timescales involved exceed human comprehension so completely that new ways of thinking become necessary. 100 trillion years already surpasses anything evolution prepared human minds to conceptualize. But the processes that follow the stellar era span periods that make 100 trillion years look like the blink of an eye. What remains after stars die? White dwarfs, neutron stars, black holes, planets flung into interstellar space when their parent stars died, and the cold, dead remnants of galaxies that once teemed with stellar life. These objects do not last forever. The same physics that created them will eventually destroy them through processes so slow that they make geological time seem rushed. Consider the white dwarfs. Trillions of them scattered throughout dead galaxies. Each one a stellar corpse containing half a solar mass compressed into an Earth-sized sphere. They possess no mechanism to generate new energy. They can only radiate away their stored thermal energy, cooling degree by degree across timescales measured in quadrillions of years. Consider the neutron stars. Millions of them spinning through the darkness, each one a cosmic lighthouse that has finally run down, their magnetic fields decaying, their rotation slowing, eventually becoming cold, dark spheres of nuclear matter drifting through the void. Consider the black holes, the final monarchs of the dead universe. Supermassive black holes in galactic centers weighing billions of solar masses. Stellar mass black holes formed from collapsed massive stars, each one seemingly eternal. Yet even black holes will not last forever. The universe's next chapter unfolds in darkness, across spans of time that require scientific notation just to write down. And each digit added to those numbers represents cosmic changes that dwarf everything that came before. The stelliferous era, our current cosmic epoch, contains everything humans have ever observed. Every star, every galaxy, every planet. Every civilization that might exist throughout the cosmos belongs to this brief window of stellar activity. When the last star dies, this window closes permanently. We exist in a temporary oasis of light within an eternity of darkness. The universe spent its first few 100 million years waiting for stars to form. It will spend the rest of time, a span approaching infinity, without them. This perspective transforms how we should view the night sky. Every star we observe is a temporary phenomenon. Every constellation is a fleeting arrangement that will dissolve as stars die, and cosmic expansion scatters their remnants. The familiar patterns that guided human navigation for millennia are cosmic accidents that will not persist. Orion will not always hunt across winter skies. The Big Dipper will not always point toward Polaris. The Southern Cross will not always guide sailors across tropical oceans. These patterns exist for only a cosmic moment, a brief configuration of nearby stars that happen to form at roughly the same time. They are already changing, and they will eventually vanish entirely. The death of stars is not some distant abstraction. It is the inevitable consequence of physical laws operating across cosmic time. The same nuclear physics that created the elements in your body guarantees that no star can burn forever. We are made of stellar corpses. The iron in your blood came from a star that exploded before our solar system formed. All were forged in stellar furnaces that burned and died across billions of years. The atoms in your left hand might have come from a different star than the atoms in your right hand. You are an assembly of matter that has cycled through multiple stellar generations, born in the cores of ancient suns, scattered by supernovae, collected by gravity into new solar systems, eventually finding their way into a biological structure capable of contemplating their origin. When the last star dies, no new heavy elements will be created. The cosmic inventory becomes fixed. Whatever matter exists at that moment represents the final accounting of stellar production. No new carbon. No new carbon. No new oxygen. No new iron. The factories have closed permanently. The death of stars marks the end of cosmic chemistry as an active process. Nuclear reactions that built the periodic table cease everywhere in the universe. The elements that enabled life and complexity become frozen relics rather than ongoing creations. This is where the universe's ending truly begins. Not with a bang, but with the quiet extinguishing of the last stellar flame. Everything that follows unfolds in darkness across timescales that stretch toward mathematical infinity. The stars are dying. They have been dying since the first one ignited shortly after the Big Bang. They will continue dying until the last one fades 100 trillion years from now. This is not tragedy. It is physics. The same physics that allowed stars to form guarantees they cannot last forever. And what comes after the stars is stranger and darker than anything the universe has yet produced. The age of light is temporary. The age of darkness is eternal. And we exist in the brief twilight between these two cosmic epochs. Witnesses to a universe that still shines, but has already begun its long descent into night. When the last star dies 100 trillion years from now, the universe does not end. It enters a new phase that scientists call the degenerate era. This epoch spans periods so vast that the entire stelliferous era, all 100 trillion years of stellar activity, shrinks to statistical insignificance. Everything humanity has ever observed, every galaxy photographed, every star catalogued, every planet discovered, belongs to a cosmic eye blink that will be forgotten in the darkness that follows. The darkness that follows stellar death is not empty. Trillions of stellar corpses drift through space. White dwarfs cool toward absolute zero. Neutron stars spin down as their rotation energy radiates away. Black holes lurk in the cores of dead galaxies, invisible against the cosmic blackness. These remnants of a luminous age persist long after the last nuclear fires have extinguished. Imagine standing on a planet, orbiting the final red dwarf, moments after it exhausts its fuel. The dim red sun that warmed your world for trillions of years has faded to darkness. You look up and see nothing. No stars punctuate the black sky. No distant galaxies glow on the horizon. The cosmic microwave background radiation has stretched to wavelengths far beyond detection. For the first time in universal history, the sky is truly black. This is the beginning of the degenerate era, and it will last far longer than everything that came before it combined. These remnants seem permanent. What could possibly destroy objects dense enough to survive the death of stars? Even the most stable structures in the universe eventually succumb to decay processes operating across inconceivable timescales. The same laws of thermodynamics that killed the stars will eventually destroy their corpses. Nothing escapes entropy. Nothing endures eternally. White dwarfs begin the degenerate era as the most common stellar remnants. Roughly 97% of all stars eventually become white dwarfs. This includes every star less than 8 times the mass of our Sun. Red dwarfs, yellow dwarfs like our Sun, and even larger stars up to that threshold all share the same ultimate fate. Trillions of these objects scatter throughout cosmic space when the stelliferous era ends. The sheer number of white dwarfs defies comprehension. Our galaxy alone will produce approximately 100 billion white dwarfs before star formation ceases. Multiply this by the 2 trillion galaxies in the observable universe. The result exceeds human counting. Approximately 200 sextillion white dwarfs. That number written out requires 23 digits. Each one a frozen stellar core drifting through eternal night. A white dwarf is essentially a giant crystal of carbon and oxygen atoms packed so tightly that quantum mechanical effects support the structure against gravitational collapse. When a star like our Sun exhausts its nuclear fuel, gravity compresses the remaining core until electrons are squeezed together at the quantum level. At this point, a fundamental property of electrons called the Pauli exclusion principle prevents further compression. Electrons cannot occupy identical quantum states. When squeezed too closely, they resist with a pressure that has nothing to do with temperature or motion. This electron degeneracy pressure supports the white dwarf against its own gravity. The object reaches equilibrium at approximately Earth's diameter, but containing roughly 60% of its parent star's original mass. The density of white dwarf material exceeds anything in normal human experience. A sugar cube-sized sample would weigh approximately 1 ton on Earth. A teaspoon would weigh 15 tons. The entire mass of the Sun's future white dwarf, roughly 600,000 Earth masses, will compress into a sphere 8,000 miles across. Matter this dense behaves according to quantum rules rather than classical physics. But white dwarfs can cool. With no internal energy source, they radiate away thermal energy accumulated during billions of years of stellar evolution. A newly formed white dwarf blazes with surface temperatures exceeding 100,000 degrees. The cooling process proceeds extremely slowly because white dwarfs are excellent insulators. Dense crystalline matter does not conduct heat efficiently. Energy trapped in the core takes enormous amounts of time to work its way to the surface, where it can radiate into space. A white dwarf is like a perfectly insulated thermos containing the heat of a dying star. Scientists calculate that white dwarfs require approximately 10 to the 15th power years to cool to temperatures approaching absolute zero. That is 1 quadrillion years. Written out, this number contains 15 zeros. 1 million billion years, roughly 10,000 times longer than the entire stelliferous era lasted. To grasp this timescale, consider that if the stelliferous era represented a single day, the white dwarf cooling period would span nearly 30 years. Everything humans have ever known about the cosmos fits within that single day. The slow freezing of stellar corpses continues for 3 decades afterward. As white dwarfs cool, they fade from visibility. First, they stop emitting visible light, becoming detectable only in infrared wavelengths. A white dwarf at 10,000 degrees still glows cherry red. At 1,000 degrees, it emits only an infrared, invisible to human eyes but detectable with specialized instruments. Then infrared emission fades. The white dwarf cools below 100 degrees, then below 10 degrees, then below 1 degree above absolute zero. Eventually, it reaches temperatures so low that no telescope could ever detect its radiation. It has become what scientists call a black dwarf. Black dwarfs represent the final evolutionary stage of sun-like stars. They are not black holes. They do not possess event horizons or singularities. They are simply cold. So cold that they emit no detectable radiation. So cold that they differ from the surrounding vacuum by only infinitesimal fractions of a degree. No black dwarfs currently exist in our universe. Not enough time has passed since the Big Bang for any white dwarf to cool sufficiently. The oldest white dwarfs in existence have had merely 13.8 billion years to cool. A tiny fraction of the quadrillion-year timescale required for black dwarf formation. We have never observed a black dwarf and never will. They belong to a future so distant that human civilization will have ended billions of years before the first one forms. But in the degenerate era, black dwarfs dominate the stellar remnant population. Trillions of these frozen corpses drift through dead galaxies, invisible except through their gravitational effects on nearby objects. The universe becomes filled with objects that emit no radiation whatsoever, a cosmos of invisible frozen spheres floating through infinite darkness. These black dwarfs will persist for timescales that dwarf their cooling period. Once cold, they have no mechanism to change further. No internal processes operate. No energy flows. They simply exist as crystallized matter drifting through expanding space. Or so it might seem. Neutron stars follow a different but parallel trajectory toward cosmic death. These objects represent the corpses of massive stars between 8 and 25 times the Sun's mass. When such stars exhaust their nuclear fuel, their cores collapse so violently that protons and electrons merge into neutrons. The entire stellar core becomes a ball of nuclear matter. A neutron star packs more than the Sun's mass into a sphere only 12 miles across. The density exceeds that of white dwarfs by factors of billions. A teaspoon of neutron star material would weigh 6 billion tons on Earth. If you could somehow transport a sugar cube of this matter to our planet's surface, it would weigh as much as Mount Everest. Neutron stars begin their existence with surface temperatures of hundreds of thousands of degrees. They glow intensely in X-ray wavelengths, invisible to human eyes but brilliant to X-ray telescopes. Their powerful magnetic fields, trillions of times stronger than Earth's, accelerate particles to near light speed. These particles create beams of radiation that sweep through space like cosmic lighthouses. When these beams happen to sweep past Earth, we detect the neutron star as a pulsar, regular flashes of radiation marking time with precision exceeding atomic clocks. Some pulsars spin hundreds of times per second. Others rotate once every few seconds. Each pulse represents one rotation of a city-sized object spinning faster than a kitchen blender. But neutron stars cool faster than white dwarfs because they are smaller and emit energy more efficiently through neutrino processes. Neutrinos are ghostly particles that barely interact with matter. They stream directly out of the neutron star's interior, carrying away thermal energy without hindrance. Within approximately 1 million years of formation, most neutron stars cool below X-ray detection limits. Within 1 billion years, they become essentially invisible to electromagnetic observation. Their surfaces drop to temperatures comparable to Earth's room temperature. Then colder, eventually approaching absolute zero across timescales, measured in quadrillions of years. The spinning motion of neutron stars also decays over time. Those powerful magnetic fields that create pulsar beams also interact with surrounding space. Charged particles in the interstellar medium create drag that slows rotation gradually. Energy radiates away as electromagnetic waves. The cosmic lighthouse dims and slows. Pulsars that spin hundreds of times per second when young slow to mere revolutions per minute over millions of years. Then revolutions per hour. Then revolutions per day. Eventually, rotation essentially ceases, leaving cold, dark spheres of superdense matter. The lighthouse has stopped spinning. The beacon has gone dark. In the degenerate era, neutron stars join white dwarfs as invisible remnants drifting through dead space. Cold, dark, inert, containing matter in exotic states that will never change through any natural process humans have observed. Processes operating on timescales beyond current imagination will eventually destroy them too, but the true monarchs of the degenerate era are black holes. When the stelliferous era ends, supermassive black holes in galactic centers have consumed much of the matter that once surrounded them. These gravitational giants weigh millions to billions of solar masses. The black hole at the center of our own Milky Way contains 4 million solar masses. Others in distant galaxies exceed 60 billion solar masses. These objects dominate the dead galaxies they inhabit. Smaller black holes formed from collapsed massive stars also populate the degenerate universe. Stars exceeding 25 solar masses end their lives not as neutron stars but as black holes. Their cores collapse completely, forming singularities surrounded by event horizons. These stellar mass black holes weigh between a few and several dozen solar masses. During the stelliferous era, black holes grew by consuming surrounding matter. Gas falling toward black holes forms swirling accretion disks that heat to millions of degrees. These disks radiate intensely across the electromagnetic spectrum, making supermassive black holes the brightest objects in the universe, despite the black holes themselves emitting no light. But in the degenerate era, the feast ends. No more gas clouds drift within reach. No more stars wander close enough to be torn apart. The accretion disks have long since drained into the event horizons. Black holes become truly black, invisible gravitational wells floating through darkness without any matter to consume. They drift through space, occasionally encountering and consuming other stellar remnants. A black dwarf that wanders too close gets torn apart by tidal forces and gradually spirals inward. A neutron star that approaches gets stretched into a stream of matter that feeds the black hole briefly before vanishing forever. But these encounters grow increasingly rare as cosmic expansion stretches distances between objects. Black holes seem truly eternal. Nothing that falls into a black hole ever emerges. The matter is lost forever behind the event horizon, a one-way boundary from which even light cannot escape. The laws of physics as understood in the 19th century suggested that black holes would persist forever. What could possibly destroy an object with such absolute gravitational control? Stephen Hawking discovered the answer in 1974. Hawking was studying quantum mechanical effects near black hole event horizons when he realized something remarkable. The vacuum of space is not truly empty. According to quantum mechanics, particle-antiparticle pairs constantly pop into existence throughout the universe. These virtual particles normally exist for only infinitesimal fractions of a second before annihilating each other and returning their borrowed energy to the vacuum. But near a black hole's event horizon, something strange can happen. Virtual particle pairs that form near the horizon can be separated by tidal gravitational effects before they annihilate. One particle falls into the black hole. The other escapes into space carrying positive energy. The escaping particle becomes real rather than virtual. It carries energy away from the black hole's vicinity. But the energy must come from somewhere. Physics requires strict conservation of energy. Nothing appears from nothing. The only source available is the black hole itself. Each escaping particle reduces the black hole's mass by a tiny amount. The energy carried away by Hawking radiation comes at the expense of the black hole's gravitational energy. Particle by particle, quantum effect by quantum effect, the black hole shrinks. This process, called Hawking radiation, causes black holes to slowly evaporate over time. The discovery revolutionized theoretical physics by connecting quantum mechanics, general relativity, and thermodynamics. It also revealed that even black holes, the most permanent objects in the current universe, will eventually cease to exist. The rate of Hawking radiation depends inversely on black hole mass. A black hole with the mass of a mountain would evaporate explosively within seconds. Its Hawking radiation would blast outward as gamma rays and exotic particles in a final detonation. But astronomical black holes are far more massive. The smallest black holes formed from stellar collapse weigh several solar masses. A stellar mass black hole of 10 solar masses would take approximately 10 to the 69th power years to evaporate completely. That number deserves emphasis. 10 to the 69th power years. Written out, this number would require 69 zeros following a 1. To visualize this duration, consider that the current age of the universe is merely 10 to the 10th power years. The evaporation time exceeds the universe's present age by a factor of 10 to the 59th power. There is no meaningful comparison from human experience. Supermassive black holes last even longer, far longer. A black hole with 1 million solar masses requires approximately 10 to the 83rd power years to evaporate. A black hole with 1 billion solar masses requires approximately 10 to the 92nd power years. The largest black holes, weighing tens of billions of solar masses, require approximately 10 to the 100th power years. This final number has a name. 10 to the 100th power is called a googol, 1 followed by 100 zeros. The timescale for the largest black holes to evaporate exceeds anything else in cosmic evolution by factors that make all previous timescales seem instantaneous. But even googol years pass eventually. In the degenerate era, time marches forward inexorably. Black holes that seem permanent on any conceivable human timescale eventually radiate themselves out of existence. The monarchs of darkness fall one by one to quantum mechanics. The final stages of black hole evaporation become increasingly violent. The process accelerates. A black hole that took googol years to lose 99% of its mass loses the remaining 1% far faster. In its final moments, the evaporation rate spikes dramatically. The last seconds of a black hole's existence produce bursts of gamma rays and exotic particles. Temperatures at the event horizon exceed anything seen since the Big Bang. The black hole explodes in a flash of energy before vanishing completely. These final detonations represent the ultimate fate of the most stable objects in the current universe. After 10 to the 100th power years, even the most massive black holes have evaporated. The monarchs have fallen. The thrones stand empty. But before black holes finish evaporating, another process begins destroying the remaining matter in the universe. Proton decay. Protons are among the most stable particles known to physics. They form the nuclei of all atoms. Every element in the periodic table contains protons. The hydrogen that fueled stellar fusion for 100 trillion years consists of single protons orbited by electrons. Protons have existed since moments after the Big Bang, and show no sign of decay under normal observation. The protons in your body have persisted unchanged for 13.8 billion years. They have survived the deaths of multiple stellar generations. They seem eternal in any practical sense, but certain theoretical physics models predict that protons are not truly stable. Grand unified theories attempt to merge the fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single framework. These theories suggest that protons can decay through processes involving hypothetical superheavy particles. The predicted proton lifetime exceeds 10 to the 34th power years. Physicists have built enormous experiments to search for proton decay. Tanks containing thousands of tons of purified water are monitored by sensitive detectors. If a single proton among the quadrillions in the tank decays, the detectors should see it. No proton decay has ever been detected. These experiments have pushed the minimum proton lifetime higher and higher, but physics does not guarantee protons are absolutely stable. The experiments establish lower limits, not absolute stability. The true lifetime might exceed current detection capabilities by factors of thousands or millions. If protons decay, the implications for the far future are profound. Every white dwarf, every neutron star, every black dwarf, every planet, every asteroid, every object made of ordinary matter contains protons. If protons decay, all these objects will eventually evaporate into lighter particles and radiation. The decay products include positrons and neutral pions. Positrons are antimatter electrons that quickly annihilate upon encountering normal electrons. The annihilation produces gamma-ray photons. Pions decay into even lighter particles within nanoseconds. The end result is that matter converts into radiation and light particles. The net effect is that ordinary matter gradually dissolves over timescales exceeding 10 to the 37th power years. Every proton has its appointment with oblivion. Every atomic nucleus faces eventual dissolution. Every structure made of atoms will crumble as its constituent protons decay one by one. This means that the trillions of white dwarfs and black dwarfs populating the degenerate era will not last forever. Proton decay will gradually erode them from the inside out. Over periods spanning 10 to the 37th power years, these objects will shrink and ultimately disappear. The frozen stellar corpses will sublime directly into radiation. Imagine a black dwarf weighing as much as our Sun. It survived the death of its parent star billions of years ago. It cooled to temperatures barely above absolute zero over quadrillions of years. It drifted through dead galactic space for eons beyond human comprehension. And then, one proton at a time, it begins to dissolve. The decay rate is incredibly slow. A black dwarf loses only a few protons per year through this process. Each decay releases a tiny flash of energy as the positron annihilates with a nearby electron. But the flashes are so dim and so rare that no detection method could ever observe them. The dissolution proceeds in perfect darkness, but the universe has endless time. Over 10 to the 37th power years, even objects containing 10 to the 57th protons eventually disappear. The sun-mass black dwarf shrinks imperceptibly over timescales that exceed the previous age of the universe by factors of 10 to the 27th power. And then it is gone, converted entirely to radiation that disperses into the void. Every black dwarf suffers this fate. Every neutron star, every rogue planet drifting through interstellar space, every asteroid and every grain of dust. All ordinary matter eventually decays through this process. The cosmic inventory of protons, accumulated through 13.8 billion years of cosmic evolution, drains away into radiation across the degenerate era. The universe enters what scientists call the black hole era. Ordinary matter has decayed away entirely. Only black holes remain as organized structures, slowly evaporating through Hawking radiation. These black holes drift through absolute darkness. No stars illuminate their surroundings. No planets orbit nearby. No matter exists for them to consume. They simply radiate quantum particles into the void, shrinking imperceptibly on timescales that make planetary geological eras seem instantaneous. The black hole era spans from approximately 10 to the 40th power years, when proton decay has destroyed all ordinary matter, to approximately 10 to the 100th power years. When the last supermassive black hole completes its evaporation, this represents 60 orders of magnitude in time. 60 such increases compound into durations beyond any description. During this era, the universe contains essentially nothing except black holes and the faint radiation they emit. The average distance between black holes exceeds millions of light years. Each one drifts in perfect isolation, surrounded by void that extends farther than the current observable universe. Occasionally, two black holes drift close enough to merge. Gravitational waves ripple outward from the collision. The merged black hole settles into a new configuration. But these events grow increasingly rare as the era progresses. Eventually, they cease entirely when too few black holes remain in any given region of space. The black hole era ends when the final supermassive black hole completes its evaporation, approximately 10 to the 100th power years from now. This moment marks the end of cosmic structure. After the last black hole evaporates, no organized objects remain in the universe. The cosmos contains only radiation and a thin gas of fundamental particles dispersed across space, expanding toward infinity. This transition represents something truly profound. For the first time since the Big Bang created matter, the universe contains no concentrated structures whatsoever. No galaxies, no stars, no planets, no atoms, no protons, just elementary particles drifting through eternal darkness at temperatures approaching absolute zero. The physics governing this final state differs fundamentally from anything humans have observed or imagined. In our universe, matter clumps together under gravity. Structures form, evolve, interact. Complexity emerges from simpler components. This organizing principle drove cosmic evolution from primordial plasma to galaxies to stars to planets to life. In the far future, this organizing principle vanishes. Gravity becomes irrelevant when no massive objects exist. The remaining particles are so dispersed that gravitational attraction cannot overcome cosmic expansion. Nothing can ever form again through any process currently known to physics. This is the heat death of the universe. Not death by fire, but death by cold. Not destruction through catastrophic violence, but dissolution through infinite dispersal. The universe does not explode or collapse. It simply spreads itself so thin that nothing meaningful can ever happen again. The particles remaining after heat death are incredibly sparse. Scientists estimate that in the far future, the average distance between elementary particles will exceed the current observable universe's diameter. Each particle will drift alone through vastness that dwarfs anything humans can conceptualize. Each electron, an island universe unto itself. Each photon, traveling forever without encountering anything. Temperature approaches zero asymptotically. The universe never quite reaches absolute zero because quantum mechanical effects maintain infinitesimal energy fluctuations. But for all practical purposes, the cosmos has frozen solid. A temperature so close to absolute zero that the distinction becomes meaningless, and yet, even heat death may not be the end. Physics at extreme timescales reveals possibilities that challenge common intuition about endings. Quantum mechanics suggests that truly random events can occur given sufficient time. In an infinite future, events of arbitrarily low probability eventually happen. Zero probability is not the same as very low probability. Given eternity, very low probability becomes certainty. This opens doors to scenarios that seem impossible under normal understanding. The darkness following black hole evaporation stretches forward without apparent limit, but hidden within that darkness, deep time continues working through physical laws that never cease operating. What emerges from that infinite future represents the strangest chapter of cosmic evolution yet to be written. The degenerate era gives way to heat death. But heat death might give way to something else entirely. Something beyond current imagination. Something that transforms endings into new beginnings. The Age of Darkness is not the conclusion of the cosmic story. It is merely the next chapter, and the chapters that follow will prove stranger still. The heat death scenario represents the most likely ending for our universe based on current physical understanding. But cosmologists have identified several alternative fates, each more terrifying than the last. The universe's final moments could unfold through multiple different mechanisms. Some gradual and cold, others violent beyond imagination. The cosmos might freeze into eternal stillness, or it might tear itself apart in a catastrophic expansion, or it might collapse back into the singularity from which it emerged, or it might simply cease to exist without warning. Scientists do not know which ending awaits us. The data remains insufficient to choose between possibilities. We live in a universe whose ultimate fate remains genuinely uncertain, and some of these fates could arrive far sooner than the distant timescales of stellar death and black hole evaporation. Understanding these possibilities requires examining the force that currently dominates cosmic evolution. A force discovered only recently, a force that remains profoundly mysterious despite decades of study. Dark energy. In 1998, two independent research teams discovered something that shocked the scientific world. Both teams were studying distant supernovae. Type 1. A supernovae occur when white dwarfs exceed a critical mass threshold and explode. These explosions produce remarkably consistent brightness, so consistent that astronomers use them as standard candles. Cosmic distance markers whose apparent brightness reveals how far away they are. By measuring the brightness and redshift of distant supernovae, astronomers can determine how fast the universe was expanding at various points in cosmic history. The expectation was straightforward. Gravity should slow expansion over time. The universe should be decelerating as matter pulls on matter across cosmic distances. Both teams found the opposite. Distant supernovae appeared dimmer than expected. This meant they were farther away than their redshift suggested. This meant the universe was expanding faster now than in the past. This meant expansion was accelerating. Something is pushing space apart faster with each passing moment. Something is overpowering gravity on cosmic scales. Something is driving the universe toward increasingly rapid expansion. Scientists named this mysterious force dark energy without truly understanding what it is. Dark energy comprises roughly 68% of the universe's total energy content. More than 2/3 of everything that exists consists of this unknown force. Dark matter makes up another 27%. Ordinary matter comprises less than 5% of cosmic contents. We are made of the rare stuff, the exceptional material, the cosmic minority. Most of the universe consists of dark components we cannot see, cannot touch, cannot directly detect. We infer their existence only through gravitational effects and cosmic expansion rates. The nature of dark energy remains one of the deepest mysteries in physics. It might be a property of space itself, a cosmological constant that Einstein first proposed and later abandoned. It might be a dynamic field that changes over time. It might be something entirely outside current theoretical frameworks. What we know is that dark energy behaves strangely. Normal matter and radiation become diluted as space expands. Double the volume and you halve the density. But dark energy maintains constant density regardless of expansion. As space grows, it contains proportionally more dark energy. The expansion accelerates. More space means more dark energy, means faster expansion means more space. This feedback loop has dominated cosmic evolution for the past 5 billion years. Before that, matter density exceeded dark energy density, and gravity was winning. Expansion slowed. Then, dark energy took over. Expansion began accelerating. The transition marked a fundamental shift in cosmic dynamics. If dark energy maintains constant density as space expands, the heat death scenario unfolds as previously described. The universe continues expanding forever. Stars die, black holes evaporate, protons decay, matter disperses into radiation, temperature approaches absolute zero. The cosmos freezes into eternal stasis across timescales measured in googol years. But what if dark energy density increases over time? This possibility leads to the most violent cosmic ending imaginable. Scientists call it the Big Rip. In the Big Rip scenario, dark energy is not a cosmological constant but a dynamic field called phantom energy. Unlike normal dark energy, phantom energy grows stronger as the universe expands. The expansion rate does not merely accelerate, it accelerates without limit, doubling, then doubling again, then doubling again. Faster and faster toward infinite expansion in finite time. As phantom energy strengthens, its repulsive effect eventually overcomes every attractive force in nature. First gravity, then electromagnetism, then the nuclear forces. One by one, the bonds holding structures together snap under the strain of expanding space. The destruction proceeds hierarchically from largest to smallest scales. The weakest bonds fail first. The strongest bonds fail last. But all bonds eventually fail. First, galaxy clusters rip apart. Galaxy clusters are the largest gravitationally bound structures in the current universe. They contain thousands of galaxies held together by mutual gravitational attraction. But gravity is weak. Extraordinarily weak compared to other forces. When phantom energy strengthens sufficiently, cluster gravity cannot resist. Individual galaxies scatter into the void, isolated forever from their cosmic neighbors. The Virgo cluster, the Coma cluster. Every great concentration of galaxies disperses into expanding darkness. Galaxies that existed together for billions of years fly apart, never to interact again. This occurs approximately 200 million years before the end. Then galaxies themselves begin disintegrating. The gravitational bonds holding stars in galactic orbits fail. The spiral arms of the Milky Way tear away from the galactic core. Stars that orbited together for billions of years fling outward into the void. The supermassive black hole at the galactic center loses its retinue of orbiting stars. Every galaxy in the universe simultaneously falls apart. Trillions of stars scatter from their galactic homes. The cosmic web that organized matter for billions of years shreds into expanding chaos. This occurs approximately 60 million years before the end. Then star systems rip apart. Planets tear away from their parent stars. Moons separate from planets. The gravitational structures that define solar systems dissolve under relentless expansion. If humanity still exists at this point, if we have colonized other worlds, if we have spread across the galaxy, none of it matters. Earth tears away from the sun. Mars vanishes into darkness. Jupiter and its moons scatter in all directions. The sun becomes a solitary star in an empty void, surrounded by nothing, orbited by nothing, alone. This occurs approximately 3 months before the end. Then planets themselves disintegrate. The expansion of space within solid matter overcomes the electromagnetic forces holding atoms together. Rocks crumble, mountains fragment, entire worlds reduce to debris. The electromagnetic force is 100 billion times stronger than gravity. Yet phantom energy eventually overpowers even this. Earth crumbles. Every continent shatters. Every mountain disintegrates. Every structure humanity ever built reduces to expanding rubble. The planet that harbored life for 4 billion years falls apart in moments. This occurs approximately 30 minutes before the end. Then, atoms rip apart. Expansion overcomes the strong nuclear force binding atomic nuclei together. Protons and neutrons scatter from atoms they occupied since the universe was seconds old. The strong force is the most powerful force in nature, 100 times stronger than electromagnetism. Yet even this cannot withstand infinite expansion. Every atom in existence simultaneously disintegrates. Carbon atoms become free protons and neutrons. Iron atoms become free protons and neutrons. Every element in the periodic table dissolves into its constituent particles. This occurs approximately 10 to the negative 19 seconds before the end. Then, subatomic particles disintegrate. Even quarks, the fundamental components of protons and neutrons, tear apart as space expands between them faster than the strong force can maintain bonds. The very fabric of matter unravels at its most fundamental level, then space-time itself might tear. Some models suggest the Big Rip ends in a singularity of infinite expansion rate. Space expands infinitely fast at every point simultaneously. The universe ends not with a whimper, but with the most violent event physically possible. The opposite of the Big Bang, creation reversed into destruction. The Big Rip completes the destruction of all matter in the universe within a finite time, not the infinite approach of heat death. Everything ends. Absolutely everything. No stellar remnants survive. No elementary particles persist. Space itself might not persist. The universe simply stops. Calculations suggest that if dark energy density grows at certain rates, the Big Rip could occur approximately 22 billion years from now. This number carries enormous uncertainty. Different models predict different timelines. Some place the Big Rip hundreds of billions of years in the future. Others bring it closer. But this timeline potentially places the Big Rip far closer than the 100 trillion year timescale of stellar death. If the Big Rip proves correct, stars will still be shining when space itself tears matter apart. The sun will still be burning. Earth might still be habitable. Life might still exist throughout the cosmos. The universe would end while still containing light. Not in the cold darkness of heat death. Not after googol years of black hole evaporation. But relatively soon, while the cosmos remains young and vital. Current observations cannot definitively distinguish between constant and growing dark energy density. The data slightly favors constant density, making heat death more likely than the Big Rip, but the error margins are large enough that the violent ending remains possible. We cannot rule it out with current measurements. The psychological difference between these scenarios is profound. Heat death unfolds across timescales so vast that they remain abstract. 100 trillion years until the last star dies. 10 to the 100th power years until the last black hole evaporates. These numbers exceed human comprehension so completely that they feel like mathematical games rather than physical predictions. The Big Rip could happen within timescales comparable to stellar lifetimes. 22 billion years is long compared to human history, but it is shorter than the Sun's remaining lifespan. It is shorter than the time remaining before the Milky Way merges with Andromeda. It places cosmic destruction within reach of conceivable futures. The opposite extreme to the Big Rip is the Big Crunch. Before dark energy's discovery, cosmologists debated whether the universe contained enough matter for gravity to eventually halt expansion and reverse it. Einstein's equations of general relativity allow for multiple cosmic geometries depending on matter density. If matter density exceeded a critical threshold, space would curve back on itself. The universe would be finite but unbounded, like the surface of a sphere but in 3 dimensions. In such a universe, expansion would eventually stop. Gravity would win its battle against cosmic momentum. The universe would reach maximum size and begin contracting. Contraction would accelerate as matter concentrated. Same gravitational attraction that slowed expansion would speed collapse. Galaxies would approach each other rather than recede. The cosmic microwave background radiation would shift from microwaves toward shorter wavelengths, first to infrared, then to visible light. Temperatures would rise throughout the cosmos. Space that had cooled for billions of years would heat again. Stars that had died would be engulfed in warming radiation. The universe would grow increasingly hostile to any form of complexity. Galaxies would begin merging. Not the graceful collisions of the current era that unfold over hundreds of millions of years. Rapid, catastrophic mergers as cosmic distances shrink at accelerating rates. Every galaxy would collide with its neighbors. Then, with the results of those collisions, then again, the night sky would fill with galaxies. Then with the merged remnants of galaxies. Then with undifferentiated light as matter compressed beyond recognition. Stars would be stripped from their orbits. Gas would heat beyond nuclear fusion temperatures. The entire cosmos would become a single expanding fireball in reverse. In the final moments of the Big Crunch, the entire observable universe would compress into a single point of infinite density and temperature. This singularity would mirror the conditions at the Big Bang. The same physics that governed the universe's first fraction of a second would govern its last. Perhaps this singularity would trigger a new cosmic expansion. The Big Crunch, becoming a new Big Bang. The universe reborn from its own destruction. This represented a cyclical cosmology where universes endlessly oscillate between expansion and contraction. Some versions of this scenario imagined infinite cosmic cycles stretching backward and forward through time. No beginning, just endless oscillation. The universe as an eternal engine cycling between creation and destruction. Dark energy's discovery effectively ruled out the Big Crunch for our universe. Accelerating expansion indicates that gravity will never overcome cosmic repulsion. Our universe appears destined for eternal expansion rather than eventual collapse. The evidence points toward heat death rather than fiery compression, but this might not be the final word. Some cosmological models propose that dark energy could change its behavior over cosmic time. What appears as a cosmological constant might actually be a dynamic field that evolves as the universe ages. If dark energy eventually reverses sign, if it becomes gravitationally attractive rather than repulsive, the universe could still experience a Big Crunch scenario. Imagine dark energy slowly weakening over cosmic time. For billions of years, expansion continues accelerating, but the acceleration gradually decreases. Eventually, expansion continues at constant rate. Then, expansion begins, slowing. Then expansion stops. Then contraction begins. The timeline for such a reversal could stretch trillions of years into the future, or it could begin sooner. The current measurements span only 13.8 billion years of cosmic history. Dark energy has dominated for only 5 billion years. We are extrapolating from limited data. Our confidence in eternal acceleration might be premature. Other models suggest that what appears as acceleration might mask deeper cosmic dynamics. Hidden variables in physics we do not yet understand. Processes operating on timescales longer than current observations can detect. The apparent fate of the universe might change as our understanding improves. The Big Bounce represents a variation on the Big Crunch theme. In this scenario, the universe contracts but does not collapse to a true singularity. Quantum gravitational effects halt the compression at extremely small but finite scales. the universe bounces and begins expanding again. Classical general relativity predicts that collapsing matter forms singularities, points of infinite density where physics breaks down. But general relativity is not the final theory of gravity. It does not incorporate quantum mechanics. At extremely small scales and high energies, a theory of quantum gravity must take over. We do not yet possess a complete theory of quantum gravity, but many theoretical approaches suggest that singularities do not actually form. The universe reaches maximum density and rebounds rather than collapsing to a point. The Big Bounce implies that our current expansion phase might be one of infinitely many cosmic cycles. Previous universes contracted and bounced before ours. Future universes will follow after ours contracts. The multiverse extends through time as well as space. Each cycle might produce different physical constants, different particle masses, different force strengths, different conditions for complexity and life. Our universe, with its particular properties, might be one of infinitely many, each bouncing cosmos exploring different possibilities. This cyclical cosmology offers a form of cosmic immortality. Individual universes end, but the meta-universe perpetuates forever through endless bouncing cycles. Our current cosmic expansion represents merely one oscillation in an eternal rhythm, one heartbeat in an infinite pulse. Some theoretical physicists find this scenario aesthetically appealing. It avoids the problem of cosmic beginnings. If the universe has always existed through infinite cycles, no first cause is required. No moment of creation from nothing, just eternal cycling through expansion and contraction. But current evidence does not support the Big Bounce. Dark energy appears to ensure eternal expansion rather than eventual contraction. Our universe seems destined for heat death rather than cyclical rebirth. The eternal heartbeat might not apply to our particular cosmic cycle, but perhaps the most terrifying possible ending involves no change to dark energy or gravity whatsoever. The existing laws of physics might contain within them the seeds of instantaneous cosmic destruction, a possibility that could end everything without warning, without build-up, without any indication that the end approaches. Vacuum decay. The quantum vacuum is not truly empty. This statement sounds paradoxical. Vacuum means empty. How can empty space contain something? But quantum mechanics reveals that even apparently empty space seethes with activity. Virtual particles constantly pop into existence and annihilate throughout the vacuum. Energy fluctuates at every point in space. Fields permeate the cosmos even where no matter exists. The vacuum is not nothing. It is the lowest energy state of these fields, the ground floor of physical reality. One of these fields is the Higgs field, discovered through the Higgs boson at the Large Hadron Collider in 2012. The Higgs field permeates all of space. It gives mass to fundamental particles like electrons and quarks. Without the Higgs field, these particles would be massless. Atoms could not form. Chemistry could not exist. Life could not emerge. The Higgs field has a particular energy value throughout our universe. This value determines the masses of fundamental particles. Electrons have their observed mass because of how they interact with the Higgs field at its current value. Here is the disturbing possibility. Our vacuum might not be in its lowest possible energy state. Quantum mechanics allows for metastable states, configurations that appear stable but are not truly at minimum energy. Imagine a ball resting in a small depression on a hillside. The ball appears stable. It does not roll. It seems to have found equilibrium, but a larger, deeper valley exists further downhill. If the ball receives enough energy to escape its current depression, it will roll down to the true lowest point. Our vacuum might be that ball in the small depression. A more stable vacuum state might exist at lower energy. Our current Higgs field value might not be the ultimate ground state. a lower energy configuration might be possible. If our vacuum ever transitions to this true vacuum, the consequences would be catastrophic beyond imagination, beyond any disaster scenario ever conceived. Beyond extinction events or stellar explosions or galactic collisions, the transition would begin at a single point in space, perhaps triggered by quantum fluctuation. The same random processes that create virtual particles might occasionally trigger something larger, or perhaps triggered by high-energy particle collision. The Large Hadron Collider accelerates particles to enormous energies. Could such collisions trigger vacuum decay? Physicists have calculated the answer. Cosmic rays have been bombarding planets and stars at far higher energies for billions of years. If high-energy collisions could trigger vacuum decay, it would have happened long ago. We are safe from our own accelerators, but we are not safe from quantum fluctuation. At any moment, anywhere in the universe, the vacuum might spontaneously decay. The probability per unit volume, per unit time, is extraordinarily small. But the universe is extraordinarily large, and time stretches toward infinity. From this point of decay, a bubble of true vacuum would expand outward at the speed of light. The bubble wall marks the boundary between our familiar physics and something completely different. Inside the bubble, the Higgs field has a different value. Particle masses are different. Force strengths are different. The rules that allow atoms and chemistry and life to exist no longer apply. Everything the bubble touches is instantly reorganized according to the new vacuum's properties. Atoms might become unstable. Electrons might become too massive to remain bound to nuclei, or too light to form atoms at all. The chemistry that allows water to be liquid, that allows proteins to fold, that allows DNA to store information, all of it changes instantly. Inside the bubble, complex structures cannot exist. Life cannot exist. Information cannot be preserved. Everything is reorganized according to new physical laws that have never been tested by evolution or chemistry or intelligence. The bubble's edge represents a wall of cosmic destruction, advancing at light speed. Nothing can outrun it. Light itself cannot outrun it because the bubble moves at light speed. Nothing can warn of its approach. No signal can travel faster than the bubble itself. No telescope can see it coming because the light from the bubble's edge arrives simultaneously with the bubble itself. One moment you exist in a universe governed by familiar physics. The next moment, that universe no longer exists. There is no warning, no preparation, no awareness of ending, simply existence followed by non-existence. If vacuum decay occurs anywhere in the observable universe, we would never see it coming. The destructive bubble could have formed billions of years ago in some distant galaxy. It could have already erased vast cosmic volumes from existence. Stars and planets and perhaps civilizations wiped out without warning, without record, without trace. The bubble could be racing toward Earth right now, traveling for millions or billions of years, crossing intergalactic voids, approaching our cosmic neighborhood. We would have no way to know. Perhaps the bubble is 1 light year away. It will arrive in 1 year, perhaps 1 light day away. We have 24 hours remaining, perhaps 1 light second away. We have 1 second left. We cannot know. We can never know. Scientists calculate that our vacuum is either absolutely stable or has a lifetime exceeding billions of years. The stability depends on precise values of fundamental constants, particularly the Higgs boson mass and the top quark mass. These values determine whether our vacuum sits in a true minimum or a metastable depression. The Higgs boson mass discovered at the Large Hadron Collider places our vacuum in a metastable zone, neither definitively stable nor rapidly unstable. We exist in a region of parameter space where vacuum decay is possible but not inevitable, where the universe might persist forever or might end tomorrow. This means vacuum decay represents a genuine physical possibility. Our universe might end not through gradual cooling or violent ripping or cosmic compression, but through instantaneous restructuring at the speed of light with no warning whatsoever. The psychological implications of vacuum decay differ from other endings. Heat death unfolds over timescales so vast they remain abstract. The Big Rip occurs over billions of years. The Big Crunch would take billions more. These endings exist in distant futures that feel disconnected from present reality. Vacuum decay could happen tomorrow, or today, or in the next second, or it could have already happened, with the destruction wave racing toward us through cosmic space right now. There is no way to prepare, no way to prevent, no way even to know. Living under the possibility of vacuum decay means accepting that existence itself rests on quantum uncertainties. The very fabric of reality might be a temporary arrangement destined for sudden dissolution. Every moment of continued existence represents a coin flip we happen to keep winning. Yet most cosmologists consider vacuum decay unlikely on timescales relevant to cosmic evolution. The universe has existed for 13.8 billion years without transitioning to a lower vacuum state. This suggests the metastable state is extremely stable, even if not absolutely permanent. The probability of decay occurring in any given volume is extraordinarily small. The expected lifetime of our metastable vacuum might exceed the timescales of heat death itself. Vacuum decay might be possible in principle, but so improbable that it never occurs before the universe dies through other means. We cannot be certain, but the continued existence of the cosmos provides some statistical reassurance. The most probable cosmic ending remains heat death. In this scenario, the universe continues expanding forever. Dark energy maintains constant density, ensuring that expansion never reverses. Stars exhaust their fuel and die. Stellar remnants cool toward absolute zero. Protons decay into radiation. Black holes evaporate through Hawking radiation. Matter disperses throughout ever larger volumes of space. Temperatures approach but never quite reach absolute zero. The universe cools asymptotically toward the coldest possible state, but quantum mechanics prevents perfect zero temperature. Infinitesimal energy fluctuations persist forever. The universe never completely freezes. It merely approaches freezing across infinite time. The heat-death universe is not truly at maximum entropy. Infinite expansion prevents the system from ever reaching perfect equilibrium. There is always room for entropy to increase slightly, but for all practical purposes, nothing interesting can ever happen again. Every star has burned out. Every black hole has evaporated. Every proton has decayed. The universe contains only photons and electrons and positrons and neutrinos, dispersed across spaces vastly larger than the current observable universe. These particles drift without interaction. The average time between particle collisions exceeds anything expressible in conventional units. Years do not suffice. Centuries do not suffice. Millions of years do not suffice. The collision timescale requires scientific notation, with exponents themselves requiring scientific notation. Each particle exists in near-perfect isolation, surrounded by void extending to distances that dwarf current cosmic scales. An electron drifting through the heat-death universe might travel for times exceeding 10 to the 100th power years without encountering another particle. Perfect solitude across perfect emptiness. Time loses meaning in this final state. Nothing changes, nothing happens, no processes unfold, no events occur. The arrow of time that governs our experience requires entropy increase. When entropy approaches maximum, change ceases. Past and future become indistinguishable. Events become arbitrary distinctions rather than meaningful progressions. The heat-death universe represents not destruction but eternal stasis. Everything that could happen has happened. Everything that could exist has existed. The cosmic story is complete. The final chapter has been written. Yet even this apparent ending might not be truly final. The laws of quantum mechanics suggest that given infinite time, anything physically possible will eventually occur. And probability zero differs fundamentally from probability very small. In an infinite future, extremely improbable events become inevitable. Fluctuations that seem impossible on any reasonable timescale become guaranteed when time itself has no limit. The universe's apparent death might contain seeds of resurrection hidden in the mathematics of quantum probability. This opens possibilities that seem to violate common sense about endings. Even in the cold, dark, empty universe following heat death, strange phenomena can occur. Phenomena that challenge our understanding of finality. Phenomena that suggest endings might transform into new beginnings. The universe's final chapters might be stranger than anything that came before, stranger than stellar evolution, stranger than black hole evaporation, stranger than vacuum decay. The mathematics of infinite time reveals possibilities that dwarf everything else in cosmic history. What happens after the end might be the strangest chapter of all. Imagine the universe 10 to the 10 to the 50th power years from now. This number is so large that writing it in standard notation would require more digits than atoms exist in the current observable universe. More digits than stars that have ever burned. More digits than all the particles that have ever interacted throughout cosmic history. The number itself is incomprehensible, yet it represents a real duration, a span of time that physics predicts will actually pass, and physics continues operating throughout this inconceivable duration. The laws of quantum mechanics do not expire. The equations of thermodynamics do not stop working. Time continues passing. Second after second, year after year, eon after eon. The universe persists even after everything we would recognize as structure has dissolved into darkness. In this incomprehensible future, something strange becomes possible. Something that challenges our understanding of endings. Something that suggests the universe's death might not be as final as it appears. Boltzmann brains. Ludwig Boltzmann was a 19th century Austrian physicist who developed statistical mechanics. This mathematical framework describes how the behavior of individual particles gives rise to the thermodynamic properties we observe at larger scales. Temperature emerges from particle motion. Pressure emerges from particle collisions. Entropy emerges from probability. Boltzmann's work explained why heat flows from hot objects to cold objects. Why gases expand to fill their containers. Why scrambled eggs never spontaneously unscramble. These phenomena arise from the overwhelming statistical likelihood of disordered states compared to ordered ones. There are far more ways for particles to be disorganized than organized. So, systems naturally evolve toward disorder. But Boltzmann's equations revealed a disturbing implication that haunted him throughout his career, an implication that extends to the far future of the cosmos. If a system can fluctuate randomly into any possible state given enough time, then eventually it will fluctuate into configurations that appear designed. Order can emerge from chaos through pure random chance, not because any force organizes the particles, but because given infinite time, every possible arrangement must eventually occur. Applied to the far future universe, this means that random quantum fluctuations can spontaneously assemble functional brains out of the particle soup remaining after heat death. Consider what this implies. The heat death universe contains only scattered elementary particles, photons, electrons, positrons, neutrinos, drifting through infinite darkness at temperatures barely above absolute zero. No structure exists. No complexity persists. The cosmos has achieved maximum entropy. Nothing happens. But quantum mechanics allows random fluctuations. Particles can briefly concentrate in small regions before dispersing again. Energy can momentarily spike before settling back to equilibrium. These fluctuations normally produce nothing of significance. A few particles clump together, then scatter. Energy concentrates, then spreads out. Noise without signal. Yet fluctuations of any magnitude are physically possible. Small fluctuations are common. Large fluctuations are rare. Enormous fluctuations are extraordinarily rare. But none are impossible. Given enough time, fluctuations of arbitrary size must eventually occur, including fluctuations that assemble functional brains. These Boltzmann brains would emerge complete with neural structures, with electrochemical activity, with something resembling consciousness. They would appear for brief moments out of random particle aggregation, experience something like awareness, then dissipate back into random particle distributions as the fluctuation dissolves. The probability of such a fluctuation is extraordinarily small. A human brain contains approximately 100 billion neurons. Each neuron connects to thousands of others through synapses. The total number of atoms in a human brain approaches 10 to the 27th power. These atoms must be arranged in extraordinarily specific configurations for the brain to function. Random processes achieving this configuration are far less likely than shuffling a deck of cards into perfect order 1 trillion times in succession. Far less likely than every air molecule in your room spontaneously moving to one corner. Far less likely than any probability you have ever contemplated. The odds against a Boltzmann brain forming through random fluctuation exceed 10 to the 10 to the 25th power to 1. A number so large it has no meaning in terms of human experience. A number that would seem to guarantee such events never occur. But infinity changes everything. Given infinite time, events of any positive probability eventually occur. Not just once, infinitely many times. A probability of 1 divided by 10 to the 10 to the 25th power is not 0. It is vanishingly small but still positive. And any positive probability becomes certainty when multiplied by infinite time. Boltzmann brains will spontaneously form countless times throughout the endless future, not hypothetically, not theoretically. Actually, the mathematics is clear. Given enough time, random fluctuations will assemble functional conscious entities from the chaos of heat death. The question is not whether they appear. The question is how frequently. Cosmologists have calculated that Boltzmann brain formation rates depend on the exact properties of the far future universe. The temperature of the cosmic background, the density of remaining particles, the rate of quantum fluctuations. Different models give different predictions. In some scenarios, Boltzmann brains become vastly more common than brains formed through ordinary evolution on life-bearing planets. The total number of conscious experiences belonging to Boltzmann brains exceeds the total number belonging to biological organisms by factors approaching infinity. This creates a disturbing philosophical puzzle. If most conscious experiences in cosmic history belong to Boltzmann brains, randomly fluctuating into existence, what does that imply about your current experience? Right now, listening to these words, thinking these thoughts, feeling whatever you are feeling, could you be a Boltzmann brain that spontaneously formed moments ago with false memories of a life history that never occurred? Your memories of childhood might be false. Configurations of neurons that arose through random fluctuation rather than actual experience. Your memories of yesterday might be false. The sense that you have existed continuously for years might be an illusion. You might have popped into existence 1 second ago, complete with false memories of everything before that moment. This scenario sounds absurd. It feels wrong at a deep, intuitive level. Surely you know you have existed for more than 1 second. Surely your memories are real. Surely you are not a random fluctuation in a dead universe. The mathematics suggest this scenario is overwhelmingly improbable for any given conscious experience. Here is why. Boltzmann brains typically possess only fragmentary, inconsistent memories. The probability decreases exponentially with the complexity of the configuration. A brain with minimal memories is far more likely to fluctuate into existence than a brain with detailed, consistent memories spanning decades. Most Boltzmann brains would experience only momentary confused awareness, fragments of sensation, disconnected thoughts, immediate dissipation, back into chaos. They cannot sustain consciousness long enough to contemplate their nature. They cannot follow arguments. They cannot read sentences. They cannot wonder whether they are Boltzmann brains. The very fact that you can follow a coherent argument across multiple sentences constitutes evidence against being a Boltzmann brain. The fact that your memories seem consistent, the fact that your experiences follow logical sequences, the fact that the world around you behaves according to physical laws, all of this requires a fluctuation so enormous that it becomes less probable than simply having a real history. You are almost certainly not a Boltzmann brain. Your memories are almost certainly real. Your continuous existence is almost certainly genuine. The probability that you arose through ordinary physical processes vastly exceeds the probability that you spontaneously fluctuated into existence moments ago. But the Boltzmann brain problem highlights something profound about the far future. Even after all structure has dissolved, even after black holes have evaporated and protons have decayed, even after the universe has achieved maximum entropy and nothing seems possible anymore, something like experience might still flicker into existence through random quantum processes. The universe after heat death is not necessarily devoid of awareness. Brief, isolated moments of consciousness might punctuate the darkness throughout infinite time. These experiences would be fragmentary, confused, appearing and vanishing like quantum foam, sparks of subjectivity in an ocean of objectivity, real but fleeting, genuine but disconnected. Imagine being one of these Boltzmann brains. You come into existence without warning. You have no past because you did not exist a moment ago. You have no future because you will dissolve in another moment. You experience only a flash of awareness, a fragment of sensation, a glimmer of something that might be called thought. Then, nothing. You dissipate back into the random particle distribution from which you arose. Your consciousness ends as abruptly as it began. No memory of you persists because there is nothing to remember and nothing to do the remembering. These entities would experience something, but what they experience defies description. No language evolved to describe consciousness without context. No philosophy prepared for awareness without continuity. The Boltzmann brain exists outside all frameworks humans have developed for understanding experience, and yet they will exist. Infinitely many of them. Throughout infinite future time. The mathematics guarantees their occurrence. Physics predicts their formation. They represent consciousness in its most minimal possible form. Awareness stripped of everything except the bare fact of experience itself. More dramatically, quantum fluctuations could potentially create much larger structures than single brains. Given infinite time, random processes could assemble entire galaxies. Consider the probability. Extraordinarily small, far smaller than Boltzmann brain formation, but still positive, still non-zero, still guaranteed to occur given infinite time. Stars could fluctuate into existence. The probability of randomly assembling 10 to the 57th particles into a stellar configuration approaches zero, but approaches is not equals. Given enough time, stars will spontaneously form from the chaos of heat death. They will burn briefly as their randomly assembled hydrogen fuses. Then they will die, adding their light to the darkness for a cosmic moment. Planets could form, worlds could appear, perhaps even worlds with conditions suitable for chemistry, for complexity, for something like life. The probability decreases exponentially with the complexity required, but no positive probability is safe from infinite time. Even entire new Big Bangs might occur through quantum tunneling events. Quantum tunneling allows particles to pass through energy barriers that classical physics would deem impassable. A particle can appear on the other side of a barrier without ever occupying the space in between. This phenomenon is not theoretical. It occurs constantly at the subatomic level. It powers nuclear fusion in stars. It enables radioactive decay. It is experimentally verified. Some cosmological models suggest that new universes can tunnel into existence through similar processes. A quantum fluctuation of sufficient magnitude could create a tiny bubble of space with different properties than the surrounding void. This bubble could inflate, expand, evolve, become a universe in its own right. The probability of such an event is so small that scientific notation fails to express it meaningfully. The timescale required exceeds anything previously discussed. We are contemplating 10 to the 10 to the 50th power years and beyond. Numbers so large that human intuition provides no guidance whatsoever. At these timescales, the distinction between probability and certainty dissolves. If something is physically possible, it will happen. If it can happen once, it will happen infinitely many times. The improbable becomes inevitable. The unlikely becomes guaranteed. Time erases all distinctions between possible and actual. This suggests that the universe's ending might not be truly final. New ordered structures could emerge from chaos. New stars could burn briefly in the darkness. New galaxies could form and evolve and die. New cosmic expansions might begin. New physics might manifest through random fluctuation. Some cosmological models propose that our own Big Bang might have originated through such a fluctuation. Perhaps our universe is not the first. Perhaps it emerged from the heat death of a previous cosmos. The random quantum fluctuations in a dead universe eventually producing a new expanding bubble of space and time. The current universe might be one quantum bubble among infinitely many, each emerging from the chaos of a previous heat death, each expanding and evolving according to its own physical laws, each eventually dying and contributing to the chaos from which new universes emerge. In this view, cosmic ending and cosmic beginning merge into a single process. Universes end in heat death. Random fluctuations within the dead universe eventually produce new Big Bangs. These baby universes expand, form structures, develop complexity, perhaps produce life, perhaps produce consciousness. Then they too die, and the cycle continues. The multiverse extends not just across space but across time. Past and future universes might stretch infinitely in both directions. No first universe, no last universe, just eternal cycling through creation and destruction, birth and death, order and chaos. Our current cosmic expansion represents merely one episode in an eternal oscillation, one heartbeat in an infinite pulse, one bubble in an endless foam of universes emerging and dissolving throughout eternity. This perspective offers a strange form of cosmic immortality. Individual universes are temporary. Our cosmos will die. Every star will burn out. Every black hole will evaporate. Every structure will dissolve. This particular universe will end. But the process itself continues forever. New possibilities unfold. New patterns of matter and energy explore new configurations. The story never truly ends because new stories always begin. Specific configurations of matter and energy last finite times. Your body will return to dust. Earth will be consumed by the expanding sun. The Milky Way will merge with Andromeda and eventually dissipate into darkness. Nothing persists, but something always exists. The void is never truly empty. Fluctuations continue forever. Possibilities remain open eternally. The universe dies, but existence continues. The cosmos ends, but reality persists. Yet, even this vision of eternal recurrence faces challenges from the deepest physics. Some theories suggest that time itself might end in the far future. This possibility is stranger than cosmic death, stranger than heat death, stranger than Boltzmann brains, the possibility that temporality itself might cease. As the universe approaches maximum entropy, the very concept of temporal succession could break down. Time is not a fixed stage on which events unfold. Time is itself a physical phenomenon, related to energy and entropy and change. When change ceases, what happens to time? Without change, time becomes meaningless. The definition of time requires events that occur before and after other events. A universe at perfect equilibrium has no before and after. Every moment is identical to every other moment. The distinction between past and future disappears. Without time, nothing can happen, including quantum fluctuations that might produce new structures. If time ends, the Boltzmann brains never form. The new universes never emerge. The eternal cycling ceases. Everything simply stops. The relationship between time and entropy remains one of physics' deepest mysteries. We experience time flowing from past to future because entropy increases in that direction. The past has lower entropy. The future has higher entropy. Memory works because recording information increases entropy. Causality operates because causes precede effects in the direction of entropy increase. In the heat-death universe, entropy change approaches zero. The universe has already reached nearly maximum entropy. Further increases become vanishingly small. The driving force behind temporal experience weakens toward nothing. What happens to time when its fundamental driver ceases operating? Perhaps time simply stops. The universe freezes into a final configuration that persists eternally without change. Not changing slowly, not changing imperceptibly, not changing at all. Perfect stasis. Absolute stillness. A frozen moment extended forever. In this scenario, no more Boltzmann brains form. No more quantum fluctuations produce structures. No more new universes emerge. The final state is truly final. Time itself ends, along with everything else. Or perhaps time continues but loses its arrow. Without entropy increase, future and past become indistinguishable. Events occur but have no temporal ordering. Causality breaks down because causes no longer reliably precede effects. The universe exists in a timeless eternal present where everything happens simultaneously and nothing happens sequentially. This scenario defies imagination. Human consciousness requires temporal flow. Our thoughts unfold in sequence. Our experiences have beginnings and endings. We cannot conceive awareness without time, yet physics suggests time might be more contingent than our experience implies. Time might end even if existence continues. These questions push physics to its limits. Current theories cannot fully describe the relationship between time and entropy, and quantum mechanics at extreme conditions. General relativity describes space-time as a unified fabric. Quantum mechanics describes events occurring in time. How these frameworks combine at the end of cosmic evolution remains unknown. The far future remains genuinely unknown. Not merely unmeasured, not merely uncertain, potentially unmeasurable. Perhaps no theory could describe conditions so far from anything we can observe or test. Perhaps the far future lies beyond physics itself. What remains certain is that our current universe, with its stars and galaxies and planets and life, represents a temporary phenomenon, a brief arrangement of matter and energy that arose from chaos and will return to chaos. An eddy in the cosmic flow, a pattern that formed and will dissolve. The laws of thermodynamics guarantee that order decreases over time. Complexity requires energy gradients that the universe steadily erases. Structure depends on non-equilibrium conditions that cannot persist forever. Everything winds down. Everything dissipates. Everything ends. We exist in a brief window between cosmic youth and cosmic death. A window that seems vast by human standards, but vanishes against the timescales we have explored. The universe was born. The universe will die. We happen to exist in between. The Big Bang created conditions far from equilibrium. Temperatures exceeding trillions of degrees. Densities exceeding anything currently existing. Matter and antimatter in nearly equal proportions annihilating each other. A tiny excess of matter surviving to form everything we observe. Life exploits those non-equilibrium conditions. Biological metabolism transforms energy gradients into complexity. Evolution builds structures of increasing sophistication by channeling entropy increase into organized forms. Consciousness itself might be a thermodynamic phenomenon, a pattern that processes information by degrading energy. As the universe approaches equilibrium, the conditions enabling life disappear. Energy gradients flatten. Temperature differences vanish. The driving forces behind biological complexity weaken and cease. Life becomes thermodynamically impossible. Humanity emerged at a particular moment in cosmic history. Not too early, when heavy elements necessary for rocky planets were scarce. Not too late, when stars no longer form and darkness dominates. We arose during the stelliferous era, the age of stars, the cosmic epoch defined by nuclear fusion and stellar light. This stelliferous era itself represents a tiny fraction of cosmic time. If we plotted cosmic history on a timeline where the Big Bang occurs at midnight and the present occurs at noon, the entire stelliferous era would last until roughly 12 hours and 1 second past noon. Everything that follows, the degenerate era, the black hole era, the dark era, all of it stretches from that point until infinity. The time after stars exceeds the time of stars by factors beyond expression. We are awakening at the very beginning of time. The universe is only 13.8 billion years old. A number that sounds vast. A duration that exceeds human comprehension. Yet the universe has existed for less than 1/trillionth of the time it will take for the last star to die. Less than 1 part in 10 to the 100th of the time until the last black hole evaporates. On cosmic timescales, the universe has just been born. We exist in the first fraction of a fraction of a fraction of a percent of cosmic history. Everything that will ever happen lies almost entirely in the future, and stellar death itself represents merely the first chapter of cosmic ending. After the stars comes darkness, measured in timescales that dwarf stellar lifetimes. After the darkness comes emptiness, measured in timescales that dwarf the darkness. After the emptiness comes the truly incomprehensible durations, where even Boltzmann brains and quantum fluctuations play out across eternities. Every human accomplishment occurs during this cosmic eye blink. Every work of art, every scientific discovery, every moment of love and creativity and meaning. The pyramids, Shakespeare's plays, the moon landing, every symphony composed, every novel written, every child born, every kindness extended. All of it happens in the universe's infancy. Your own consciousness listening to these words happens in this brief window. This moment of awareness exists in the thin sliver of cosmic time when complexity remains possible, when stars still burn, when life can exist, when minds can form and contemplate their own existence. This perspective can feel terrifying. Cosmic time renders human experience insignificant. Our entire species exists for a duration that rounds to zero on cosmic timescales. Everything we value will be erased. Everything we build will crumble. Everything we are will be forgotten in darkness that stretches toward infinity. The universe does not care about human concerns, does not know we exist, does not preserve our memories or honor our achievements. The cosmos proceeds according to physical law, without regard for meaning or purpose or value. Stars burn and die, galaxies collide and merge, black holes evaporate, entropy increases, and none of it cares about the brief flicker of awareness that occurred on one small planet, around one ordinary star. But another perspective is possible. The universe's ability to produce observers who can contemplate its fate represents something remarkable. For billions of years, matter simply existed without understanding itself. Atoms formed and reformed, molecules combined and separated. Stars burned without knowing they burned. Galaxies collided without awareness of their collision. The cosmos evolved in perfect ignorance of its own existence. Then on at least one small planet, orbiting one ordinary star in one typical galaxy among 2 trillion galaxies, matter organized itself into patterns capable of asking questions. Where did we come from? Why does anything exist? How will it all end? These questions might have no ultimate answers. The universe did not create itself for our benefit. We are not the purpose of cosmic evolution, not the goal toward which 13.8 billion years of history aimed. We are products, side effects, temporary arrangements of matter that happen to have the capacity for self-reflection. But we are products capable of comprehending the product line. The universe has developed eyes with which to see itself, minds with which to understand itself, hearts with which to feel awe at itself. Every piece of information humanity has gathered about cosmic endings represents matter, contemplating its own fate. The calculations of stellar evolution, the predictions of black hole evaporation, the models of heat, death, and vacuum decay. All of it is the universe thinking about its own future. Through the medium of human consciousness, the atoms in your brain were forged in stars that died before the sun was born. Carbon and oxygen and nitrogen created through nuclear fusion in stellar cores, scattered through supernova explosions across interstellar space, collected into the gas cloud that formed our solar system, incorporated into the planet that would become Earth, organized through billions of years of evolution into a configuration capable of understanding stellar nucleosynthesis. Those atoms have assembled into a brain that can comprehend stellar death, black hole evaporation, heat death, Boltzmann brains. The very matter created in cosmic processes has organized itself to understand those processes. The universe has become conscious of itself through you. This is extraordinary. This is precious. This is happening right now in this brief window when the universe remains young enough to support observers. The cosmic endings we have explored span timescales that reduce human civilization to mathematical insignificance. Our entire existence disappears into rounding errors. Our greatest achievements vanish into noise. Our deepest meanings dissolve into the darkness that follows. But within those timescales, we exist. We think. We wonder. We feel. We create meaning, even knowing that meaning will not persist. We build civilizations even knowing they will crumble. We love even knowing that love will end. This is not futile. This is the only possible response to cosmic reality. We cannot extend our existence to cosmic timescales. We cannot preserve our achievements against entropy. We cannot make the universe care about human concerns, but we can exist while we exist. We can think while we can think. We can love while we can love. We can find meaning in the brief window available to us. The universe's final moments stretch across durations that make eternity seem brief. Stars will die 100 trillion years from now. Black holes will evaporate across googol years. Matter will decay and disperse. Darkness will fall across timescales beyond expression. And yet before all of that there is now. There is this moment of awareness in a cosmos that will mostly remain unaware. Most of cosmic time contains no consciousness, no observers, no understanding. The universe exists in darkness and silence and ignorance for almost all of its duration. But not now. Now there is awareness. Now there is understanding. Now there is wonder. There is this brief candle of consciousness in an ocean of darkness, burning for an instant on cosmic scales, illuminating nothing on cosmic scales, mattering to nothing on cosmic scales, but burning nonetheless. There is us, asking impossible questions and finding partial answers that lead to deeper questions, building knowledge that will not persist, creating beauty that will not survive, loving fiercely in the face of certain loss. The universe ends in silence. This is certain. The physics is clear. Every equation points to the same conclusion. Entropy increases. Order dissolves. Complexity fades. And finally nothing remains but scattered particles drifting through infinite void. But before that silence falls, there is music. There is thought. There is love. There are minds capable of contemplating infinity, and hearts capable of breaking at its vastness. We are the universe experiencing itself before the lights go out. The cosmos has produced observers exactly once in the region we can see. Perhaps life exists elsewhere. Perhaps consciousness has emerged on other worlds. But here, now, certainly, awareness exists. This awareness will not last. Humanity will end. Earth will end. The sun will end. The galaxy will end. All structure will end. The awareness that currently exists will be extinguished along with everything else. But right now, it exists. Right now, you exist. Right now, this moment of cosmic self-reflection is occurring. The death of the cosmos is certain. Every star will burn out. Every structure will dissolve. Every possibility will eventually actualize and then fade into eternal emptiness. But right now, in this moment that exists between the Big Bang and the Big Freeze, there is something rather than nothing. There is wonder. There is curiosity. There is the remarkable fact of existence examining itself. And that wonder matters. Not because the universe cares. The universe does not care. Not because it will be remembered. It will not be remembered. Not because it changes cosmic outcomes. It changes nothing. It matters because we care. Because meaning exists for us even if it exists nowhere else. Because value is real to the beings capable of valuing. Because wonder is genuine to the minds capable of wondering. The final moments of the universe will arrive eventually. When they do, nothing will be there to witness them. No consciousness will observe the last black hole evaporating. No mind will contemplate the final quantum fluctuation before time loses meaning. The universe will end without audience, without understanding, without awareness. The same way it existed for billions of years before consciousness emerged, alone. But before that ending arrives, there is this. There is you. Having journeyed through cosmic timescales that stretch toward infinity, having contemplated the death of stars and the evaporation of black holes and the long darkness that follows, there is this moment of connection between one conscious being and another across whatever distance separates us. You listen to these words. Someone, having said them, understanding passing between minds. This connection too will end. These words will be forgotten. These thoughts will dissipate. These minds will cease, but not yet. Right now, understanding exists. Right now, connection exists. Right now, consciousness contemplates its own cosmic context and feels something in response. The universe will end in silence. But not yet. Not yet.